So, today's discussion is on bungee jumping cord. So, it is a post product. Now, let us say that we need to develop a safe bungee jumping rope or cord for human of average weight 75 kg, and the jumping height is 30 meter. So, how to design? Now, what we are going to discuss is based on a research paper written by J. W. Kuckelman and M. Hubbard. The title of the paper is Bungee Jumping Cord Design Using Simple Model. So, let us discuss this. This is a very interesting research paper, and it is going to really give you an idea, that is how to design a product something like this, and we will find that this can be used in other types of similar product. So, if we look at the design data for this, what is given to us is the weight of the human or the mass of the human, which is 75 kg. Height of the jump is 30 meter. So, the jump could be from a cliff or from a bridge on a river, so that there is enough space downwards. So, 30 meter space is available. So, design parameters we need to be found out is rope thickness or rope diameter, the rope length that we need, and what should be the rope material. Now, the requirement is that there should be low G forces, gravity forces should be low, otherwise the human being is going to be hurt. So, you need a very low G forces which is tolerable. There has to be a very high safety factor, that the cord is not going to fail, and design variables in this case are cord thickness or cord area or cord diameter, whatever we can say, and the length of the cord that we should use. Now, here is a one dimensional model of the jump. You can see on the right hand side a simple schematic is shown, where the jumper is here. There is a cord attached to the jumper, and the cord is connected to this point. The length of the cord, the extensibility of the cord, and the total length including extensions are all shown in the diagram. So, one end of the cord is connected to the top of a structure, and the other end is attached to the CG of the jumper by some harness. So, initially the CG of the jumper and is at the same elevation where the cord is connected. Now, let m be the mass of the jumper, g is the acceleration due to gravity, L is the length of the cord, k is the spring stiffness of cord, x is the stretch of cord, h is the total height fallen. Everything is given on the right hand side of the diagram. It is a very simple sketch. So, what we can write from the schematic, that h is going to be L plus x, where L is the length of the cord without stretch. So, as the person jumps and he falls by a height of L, then onwards only the cord starts elongating, and it keeps on elongating till the entire energy is absorbed by the extension of the cord. So, therefore, H is L plus x as shown in the diagram, very clear, and from the conservation of energy we can write that initial gravitational potential energy should be equal to elastic potential energy of the cord, and therefore, mgh is going to be half k x square. Then from there we go for the model of the cord. The Bungee cords are made of natural rubber, as it has very high elongation. So, it has to extend a lot, because the energy of the person who is going to jump has to be absorbed. So, extension is one of the most important requirement, and the material that extends a lot is natural rubber or other synthetic rubbers. Now, the stress strain diagram of a natural rubber is shown on the right hand side. Strain versus stress diagram is shown. So, you see the natural rubber has a strain, breaking strain of almost 6, that means it can extend 600%, that is the stretchability. The synthetic rubber which we use, one of the very extendable material that is used in textile is spandex or lycra. They also have very high extensibility, and we know that we make use of them in many textile products in order to develop stretch. Like stretch denims are very popular. Similarly, wherever we need a little bit of stretch in order to make the product comfortable, we use lycra or spandex, but here it is normally natural rubbers are used. So, natural rubber, if you look at stress strain diagram, it is nonlinear in nature. So, stress and force relationship we all know from the basic physics, that stress is force by area and strain is extension or by original length or elongation by original length, and modulus of elasticity is the ratio of stress by strain. So, these are from very basic definitions which you all must be knowing. From here we can write that force equal to stress into area. If stress is modulus into strain. So, modulus into strain into area, and that we write strain we write as at x by L. So, we are simply substituting them and arrive at this, that F is equal to k x, where k behaves like a spring constant. We are also very you also know that in the case of spring, as we stretch the spring, the force that we require to stretch a spring by x is F is equal to k into x, and k we call spring constant. Here also it is similar. Now, relationship between modulus and stiffness k. What is k? K is actually A E by L. We have replaced k. This A E by L, this whole thing has been replaced as k. So, the modulus is E and stiffness k is A E by L. So, elastic modulus is a material property which is independent of area and length, but stiffness depends upon elastic modulus. It also depends upon area and also depends upon length. Then we go to the next page, next slide. We need to meet very low g force. G is the G force basically means the acceleration that a person is going to experience when he is going to fall, and then the reverse force that he is going to experience, because the cord is going to extend. So, we need to meet a low G force and very high safety factor. Let the maximum tolerable force be F max. So, cord stiffness K equal to F max by x. Now, substituting the value of K in equation 2 earlier, which was mgh into half k x square. This was the original equation, equation number 2. We simply substitute the value of k as F max by x, we get this F max by 2 into x, and F max by mg becomes 2 h by x. H is replaced by L plus x, and then L by x equal to 1 by strain. So, if we carry on this, it is 2 into 1 plus epsilon by epsilon. So, F max by mg is this equation, and F max by mg is the G force, that is the person is going to experience when his velocity is going to be retarded. So, that is a human being has a tolerance. If the G force is very high, there could be a lot of difficulties for the person. In extreme situation, the person can even get injured. Now, what we need, that this ratio F max by mg should be within the tolerable limit, and F max by mg is a function of strain. So, in the next slide, we are stating about G force tolerance. So, we have plotted G force versus strain from the previous equation, and you look at this graph. It shows a rapid increase in G force for smaller train. When the strain is less, as we go towards 1, see from 2 onwards, if I go this side, the strain, the G force is going to increase very high. It is going from 2 to 4, 4 to 6 to 8 to 10 times. That means, if the extensibility of the cord is restricted, then the person is going to experience very high G force, and therefore, he may get injured. At a larger strain, G force approaches 2. So, larger strain means what? Larger strain means this greater than 3, not less than. In this region, the value of G is close to 2. So, G force tolerance depends upon the force orientation, magnitude, duration, and rate of onset. In body harness, the jumper body is oriented upright when it jumps and has experienced a positive G force. That is, when a jumper is jumping, his head is up and the legs are down. That posture basically means that his orientation is upright. In the ankle harness, when the harness is attached to the ankle, the jumper orientation is upside down, just opposite, and experience negative G force. Humans are less tolerant to negative G force. The bungee jumping G force should be less than 3. So, the force has to be less. This is the force where it is 3. It has to be less than this side on the right hand side, from here to there. That means, the strain level has to be 2 or more. So, now we can write certain design equations. Relation between unstretched chord length and chord strain. H is equal to L plus X, we have already seen it. Since strain is X by L, so elongation X is L into strain, original length of the chord multiplied by strain. So, H we can write, if we substitute the value of X, we get this, and therefore, length of the chord in an unstretched state is going to be H by 1 plus strain, and chord cross sectional area we have already seen equation 6, which looks like this. From there we have seen what is F, force is equal to stress into area. So, stress into area divided by mg is going to be this one, just substitute the value of force, and from there if we write what is my chord area A, we can write this, and we end up with this equation that A is equal to 2 mg 1 plus epsilon by capital E epsilon square. So, chord area depends on these parameters, weight or mass of the person, the initial modulus of the chord, and the strain level, how much strain the chord is going to experience. These are the parameters which is going to decide the chord area. Now, we are going to estimate the design variables, that is what is should be the area of the rubber chord that we are going to choose. Now, G force should be less than 3, so that the person can, it remains within the tolerable limit of the human. This means the elongation has to be more than 200%, like it is shown here in this diagram. G 3 is here, and suppose the elongation region is should from here to there, it should be at least 200% or more than that. And in that equation A, if we put these values, m 75 kilo, modulus we need to find out depending upon which rubber we are choosing. So, in this given example, the stress strain diagram that we have seen earlier, the modulus in the initial region, in the first strain level up to I think 3, it is almost linear. So, we are using actually that part of the stress strain curve where the stress and strains are proportional to each other, otherwise it is basically a non-linear relationship. So, from there the value of E is this, elongation limit we have to keep it at 2, that means 200%, strain is 2, because it has to be 200% or more, not less than that. So, if we put it at 200% elongation, then that means as a lesson the strain is 2. So, we put the values in this equation, and from there we get a figure, the area is 1.546 to the power minus 3 meter square, and this is equivalent to 16 centimeter square. So, we have to choose a rubber chord whose area has to be 16 centimeter square. From there we can calculate the diameter also now, because pi d square by 4 equal to 16. From there we can easily calculate what should be the diameter of this rubber chord. From here we go to the next slide. Now comes problems, that is a jumper weights varies, we do not know what is going to be the weight of the jumper. So, we started with designing for a jumper assuming his weight is 75 kilo. But if we want to satisfy a wide range of jumpers whose weights may vary, so whatever we have till now designed for a 75 kilo jumper, it will work also for a jumper which is who is less than 75 kilo. So 70 kilo, 65 kilo, 60, it will not really be a problem, because we have taken care of the weight up to 75 kg. So, if it is less than that, there is no issue, but there are people who could be heavier. So, let us say the mass range of jumper is plus minus 15% of the mass of the ideal jumper who stretches the cord by 200%. So, for the mass range of jumper 75 plus minus 15, that means it is going to be 64 kg to 86 kg. That is the range of weight. So, 75 kilo and above, 75 kilo and less, there is no issue, but for more weights we have to find out whether it will be able to satisfy or not. Now, the cord strain for the heaviest jumper is Z equal to mg by AE. See, from the previous equation, mg by AE we are trying to find out, we are replacing it by a constant Z. So, mg by AE is 0.7644 based on the weight of the person and the area of the cord that has been already developed or we have already found out. From there, we will see that the strain is going to be this much. That is, if we go back and look at this estimation of cord strain, then cord strain, see this is the equation which is connecting area of the cord with the weight and strain which I have already seen. From there, simply expanding this, we can write from 7 epsilon square is 2 mg 1 plus epsilon by AE, the same equation, and now what are we doing, that we are replacing mg by AE by Z, it is becoming 2 Z into 1 plus epsilon, and from there we can write this is the quadratic equation of strain, and from this quadratic equation we can find out what is the value of strain. Strain is going to be Z plus minus root over Z into Z plus 2. This is the strain, where Z is the constant and Z is mg by A into E. Cord mass per unit length, if we want to find out, it is S into rho W into A into L. The idea is that if it is a circular cord, if we want to find out the weight, we need to know the volume multiplied by density. So, A into L is the volume, S is the specific gravity, and this is the density of water, and hence this becomes your the weight per unit length of the cord. So, the strain is this equation number 10. So, if we go back to the same equation, you use that equation to find out what is the strain in this case. We will find out, if we substitute the value of Z here, we get a figure 2.218. That is, cord elongation in the case of this 86 kg mass is going to be 222%. Now, let us assume that a jump structure has a height which is more than 30 meter, because if we are thinking that at least it should be 30 meter in height when the person jumps and the cord get extended. So, the total height available is at least 30 meter, and the heaviest jumper is going to stretch the cord by 30 meter. Therefore, the unstretched cord length is going to be how much? We put this value from the previous equations, is going to be 9.32 meter. That means, we need a cord length of 9.32 meter, and cord mass we can also work it out. It will give you a figure 13.8 kg is the weight of the entire cord of 9.32 meter. So, you know this is the cord length, this is the weight, and with this length if we choose the cord, even the heaviest person will be able to survive, because he is not going to experience a G force which is greater than 3, because it has to be less than 3. With this we close today's discussion. That is, this gives us a very interesting idea that how to approach in designing let us say mountaineering ropes also. We can extend the same principle of the design that we have discussed with the bungee jumping cord. It can be extended to mountaineering ropes also. The similar situation may arise there also. The rope which we have discussed here is only the rubber part. That is the main part which is actually playing its role. That is crucial element. But obviously, the rubber has to be then covered. So, rubber is covered by some textile material which will protect the rubber. Natural rubbers are susceptible to sunlight, and they can get abraded very fast if it comes into contact with abrading surface. Therefore, all these cords, the rubber is there at the core, and there is a sheath which is made of some textile fibers, or generally filaments. Mostly it is nylon. So, it will be entirely covered by the nylon. The rubber part will be inside, and the purpose of this sheath is to protect it from abrasive damage and from UV or from other chemicals with which it may come into contact. So, that part of the design of the sheath part we have not discussed here is the main crucial element is the rubber cord that we are going to use, and how to find out the design variables of this rubber cord. Thank you.